Afternoon, Algebra 1 students. We're going to jump ahead to the lesson 13. We're asked to graph each function and identify the key functions, key features of the function, rather. So let's start with y equals 2x plus 1. So this is in the form of y equals mx plus b, by the way, such that slope m equals 2, the b, which is the y-intercept, equals 1, and then y is whatever we, dependent on what we put in for x, will determine what we get for y. And we can think of any function or relation kind of like a little machine. Put in some x, it goes through the machine, and then it comes out a y. That's our output. This is our input. Again, x and y are just generic terms. So specifically with regard to b equals 1, the y-intercept, y-intercept is going to determine where we start out on the y-axis. So it's where the graph crosses the y-axis. And we might as well plug that in. That's one of the key features we're asked to input, identify, and we can do that on the graph and also answer that at the same time for one of the key features. And in tabular form, that means when x equals 0, what is y? So if we plug in x for 0, that'd be 2 times 0 plus 1. 2 times 0 is 0. 0 plus 1 is 1. So we can safely say that the y-intercept is 1. So right over here, 1. Then the slope, in this case, m, you see that we have 2, m equals 2. M equals 2, as we stated, but specifically that's 2 over 1. So rise over run. M is rise over run. So we go up 2 and over 1. So 1, 2, 3 over 1. And then go up 2 and over 1. Up 2 and over 1. Up 2 and over 1. And up 2 and over 1. And I'm just going to make that the kind of the end of an arrow. And then if we went down 2 and over 1, then down 2 and over 1, 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 down 2 and over 1. So now we have a line. It's a linear equation. Linear means straight line. If someone thinks in a linear way from A to B to C to D, that's a geometrical, mathematical way of saying it's a straight line. So it's a straight line, which also, you see there's one straight line. There's not a curve. There's not a point where two straight lines meet, or a curve meets another curve, nothing like that. So definition of a vertex in geometry, a vertex is a plural, meaning more than one. Vertices, or vertexes is a point where two or more curves, lines, or edges meet. Like that would be, or that. And see, there'd be this line, this point in red, and in green where the two kind of meet, and the vertex would be right on top, or over here, the vertex would be right here on the bottom. But there's nothing like that here. It's just one continual straight line from A to B to C to D, and so forth. So we can say for the vertex, back to black, just none. And then erase all this. We know that as we established, the y-intercept is where y equals 1. There's no vertex because it's a straight line. And then for the domain, by the way, is a territory over which dominion is exerted from Middle French domain, estate, from medieval Latin domainum, domain, estate, from Latin dominium, property, dominion, from dominus, lord, master, owner, from dominus, house, household, a latter borrowing from French of the word which became demens, a sense of dominion again, or province of action, meaning range, well, quote unquote, range or limits of any department of knowledge or sphere of action. Anyway, so think of it like a map going from west to east, from left to right, but it's just going in a straight line from left to right along the x-axis. How many houses down the street are you going to go? How many blocks are you going to walk until you reach your friend's house? So domain on this, we're moving from left. We're going towards negative infinity on one side of the street. Negative infinity. And as we move to the right, we're moving towards positive infinity, but there's no restriction in either direction. So we can safely say that x equals all real numbers. And then as far as range, think of that like mountain range. For instance, I live in the shadow of the Sierra Nevada mountains in Reno, Nevada. So that's a mountain range going up. And that's like the y-axis, going up on the y-axis from bottom up. And if we go down, like negative infinity, and move up towards positive infinity, there's not really any restriction there either, is there? As each value, as we keep getting bigger, as we move to the right, produces a higher value going up. But if we went in the opposite direction and we went down, we just keep going to a lower, we kept going to the left, we'd keep going to a lower and lower value going down the y-axis, but there's not anything that's restricted. We're just going as far down towards negative infinity going down, and as far up towards positive infinity as we're going up. So the range would also be y equals all real numbers. There's no vertex, and then the x-intercept, well, just like we said, the y-intercept is where the graph crosses the y-axis. The x-intercept is where the graph crosses the x-axis. And we can sort of see that somewhere between 0 and -1. But where exactly is it? Well, instead of plugging in 0 for x, we're going to plug in 0 for y, because the x-intercept is where y equals 0, we're trying to figure out what x is. So if I have 2x plus 1 equal to 0, instead of equal to y, it's equal to 0, and I subtract 1 on both sides, so I'm going to end up with 2x equals negative 1, and then I divide both sides by 2, that's going to be x equal to negative 1 half. So negative 1 half, x equals negative 1 half. And again, that kind of makes sense. Right over here somewhere, there's negative 1 half. So it's right there, smack in the middle of that spectrum between 1, negative 1, and 0, negative 1 half. And then an asymptote, we could think of, I've drawn out a little blueprint of this algebraically, but I'll just redo that. But the definition is an asymptote is a line that continually approaches a given curve but does not meet it at any finite distance. So it's continually moving towards it, but it never actually reaches it. And typically when we're dealing with asymptotes, we're dealing with ratios, which is just another way of saying a fraction. It's the ratio of one thing into another, which can be written as a fraction. So if I had 2x divided by x squared minus 4, well, the first thing we would do is factor. So x squared minus 4 is the difference of squares, because x squared is just x times x, and 4 is just 2 times 2, but it's also negative 2 times negative 2, so we could rewrite that as the denominator, that is, and, well, the numerator at the same time. We're going to have 2x over x minus 2 times x plus 2. All right, so now the second step is to cancel out any like terms. If there was something up here, we can't really factor 2x anymore, but if we had a x plus 2 or an x minus 2, we could cancel one of them out. We don't have that, so nothing to do with canceling. And then the next thing is to set everything equal to 0, or the denominator equal to 0. So set denominator equal to 0. And then that's the same thing as x minus 2 equals 0 and x plus 2 equals 0. You just add 2 to both sides and then subtract 2 on both sides. So you're just going to end up with x equals positive 2, or just 2, and x equals negative 2 as your two vertical asymptotes. So it means that where x equals negative 2, you'd have a dashed line that it never crosses, and then where x equals positive 2, you'd have another dashed line where the graph never crosses. So something like this, and then something in the middle. But in the case of this particular equation, we don't have an asymptote. There's nothing restricting it. It's not a ratio other than it's divided by 1. It's 2x plus 1 divided by 1 technically. But no, there's no asymptote, so none. And then, like we alluded to earlier when we were talking about the domain and range, as we move along to the right, each y value keeps going up. So it's increasing between negative infinity and positive infinity. We use parentheses because it never reaches negative infinity as we move to the left on the x-axis, and it never reaches positive infinity as we move to the right on the x-axis. But the point being, we're focused on whether or not the y value will be increasing or decreasing as we do so, and that also never reaches negative infinity or positive infinity. So it's increasing. the whole time. It's never decreasing. So not decreasing. And then problem 2 is more complicated or perhaps more interesting. We're dealing with y equals the absolute value of x minus 4 minus 2, which means we can use the following blueprint. A times x minus 4, absolute value of x minus 4, plus k, where a equals 1, and oh, I put in 4 there, but I meant to say x minus h. H equals 4, and then k equals negative 2. So focusing on k, negative 2, that's telling us that's a set of directions on what we're going to do on the y-axis. So it means that our vertex is going to start at the point where y equals negative 2. So negative 1, negative 2, somewhere along here is where we're going to start. But where do we start on the x value? Well, it's where x minus 4. So we're going to do the opposite of whatever it says inside. And the reason is much like what we were doing over here in finding the vertical asymptote if there had been one, and we solved for what x equals. That's essentially what you're doing with the absolute value function as well. So you would solve for what x equals is the point, and so you do the opposite. So instead of negative 4, it's positive 4. So we move to the right 4 spaces. So we're going to start where x equals 4, y equals negative 2. And we could even make a little table. Or let me put it over here. And start out at 0, 1, 2, 3, 4, 5, 6, 7, 8. Where x equals 4, y equals negative 2. And then a equals 1, as I stated, because there's not any number over there. So the absence of a number on the outside of the absolute value in that function just means it's a 1. So that means 1 over 1. So a equals 1 over 1. Is 1 over 1, rise over run. So that means that if we start at our vertex again, where we have 4 and negative 2, because that's our vertex, we're going to move up 1 and to the right 1, and then move up 1 and to the right 1, and then up 1 and to the right 1, and then over here, up 1 into the right 1, and then up 1 into the right 1, and then up 1 into the right 1, and then up 1 into the right 1. So we have our V-shaped graph. It's also the flight pattern birds make, right? Okay. When birds are in a migratory flight, they have this V-shaped trajectory to their flight pattern. Anyway, we have this V-shaped curve, and we can even check our points. So when x equals, say, 5, when we have 5 minus 4, we're turn x into 5. And the absolute value is minus 2. 5 minus 4 is 1. 1 minus 2 is negative 1. So that would make sense. And it's 5. We're right at negative 1. Right at negative 1. And you can see that negative 1. On the other side, where x equals 3. 3 minus 4. That's negative 4 plus 3 is the same thing as 3 minus 4. So that's just negative 1. The absolute value of negative 1 is positive 1. 1 minus 2 is the same thing as negative 2 plus 1. So that's just negative 1. And then that means when x equals 2, 2 minus 4 is negative 2. Negative 2, and if I have 2 minus 4, that's going to equal negative 2. Negative 2 plus 2, or minus, well, the absolute value of negative 2 is positive 2. So 2 minus 2 equals 0. And same thing over here, 6. If I substitute in x for 6, 6 minus 4 is 2. 2 minus 2 equals 0. And then 7. 7 minus 4 is 3. Absolute value of 3 is 3. Absolute value of positive 3 is 3. 3 minus 2 equals 1. And then 8. 8 minus 4. 8 minus 4 is 4. 4 minus 2 equals 2. And other direction, 1. 1 minus 4 is negative 3. Absolute value of negative 3 is positive 3. 3 minus 2 equals 1. And then 0 when x equals 0. 0 minus 4 is negative 4. Absolute value of negative 4 is just 4. 4 minus 2 equals 2. All right, that makes sense. When x equals 0, we're right at 2 over here. So that's our x-intercept because that's where the graph or that's our y-intercept. That's where the graph crosses the y-axis. When x equals 0, y equals 2. So y-intercept, y equals 2. We have two x-intercepts where the graph crosses the x-axis at x equals 6 and x equals 2. So x equals 2 and 6. And then asymptote, there really isn't an asymptote. So none. And then increasing, well, we can see that between positive 4 over here, going up, as we move to the right from positive 4, each value of y keeps getting bigger and bigger. So we can say between 4 and positive infinity, because we are including 4, so it's in brackets, but we never reach infinity, so that's in parentheses. We can say that that's where it's increasing. And then for decreasing, we can see that, as each x value moves to the right, going from negative infinity, each y value is getting smaller and smaller until we hit 4. So at that point, between negative infinity and positive 4, again in brackets, then that's where it's decreasing. And then as far as the range, well, the range going up, we go as high as positive infinity in this direction. and as I is positive direction on the other vertice, but we never go below 4. So the range is really between 4 in bracket and positive infinity. Between 4 and infinity, but the range, excuse me, not 4, but negative 2. Between negative 2, it never goes below negative 2. So that's as low as we go, and then we go as high as infinity. And then on the other end, or the last item, which is the first item actually, domain, well, is there any restriction on the left? Any x we couldn't enter? That's in the independent variable, the input. We could have pi even on this graph. We could have negative pi. We have all kinds of irrational numbers. It can be any real number. So again, x would equal all real numbers. That's it for those two problems.